Okay, let's finish notes for chapter 2.1. Uh, we went over the general or the limit definition of the derivative and how to apply that. What I skipped over was the alternative definition, derivative definition. And this derivative definition allows us to find the slope of the tangent line to the curve at a point directly. So this formula does not get us to the derivative function, but instead it will find the slope of the tangent line to the curve directly. So the rule is f prime of c, c being the x value that we want to evaluate the slope for the function. Limit as x approaches c of f of x minus f of c over x minus c. So you see there is a slope element to this formula as well. Okay. So let's look at an example of that. So let me just start off with example 4 here. So use the alternative definition, derivative definition, to find the slope of f of x equals root x at x equals 2. So here is our alternative definition. X equals 2, so this is the target x value that we want to find the slope for this function. So we should say c is equal to 2, but x equals 2 is fine as well. So I'm going to plug 2 in for c. So every c value gets replaced with 2. So this c becomes 2. I want to find f prime of 2. I want to find the slope of the tangent line to this curve of root x. Limit as x approaches 2, f of x, which is root x, minus f of 2 all over x minus 2. So now we're going to treat this like we would a limit problem, algebraic steps involved. We're going to plug 2 in for x first. But first, f of 2 becomes root 2, because if I plug 2 into the original function, I'm going to get root 2. So that leaves me to this form. Limit of x as x approaches 2 of root x minus root 2 all over x minus 2. So now if we plug in 2, we're going to get root 2 minus root 2 all over 2 minus 2. So we get 0 over 0, which means that this is indeterminate. We can do something to help us cancel out this x minus 2 in the denominator. Okay. So we see radicals in the numerator. We can go through the conjugate method. So multiply by the conjugate of the numerator. So root x plus 2 all over root x plus 2. We expand. We're going to get x minus 2 in the numerator. Denominator gets us x minus 2 times root x plus root 2. The x minus 2's cancel out. We're left with 1 over root x plus root 2. Now we can plug in the remaining x with 2. So root 2 plus 2 becomes 2 root 2. And so this is our derivative. So this jumps directly from the function and the ordered pair into the slope of the function. So the slope of the function at 2 will be 1 over 2 root 2. Okay. Let me go back to example 3. So this goes back to finding the derivative of root x at x equals 2, now using the limit definition, the general definition. So the general definition is going to first arrive at the derivative function, and then we can take the additional step to find the slope of the function by plugging 2 into the derivative. So here's our limit definition, general limit definition. We're going to plug, we're going to evaluate the f of x plus h. So what this means is we're going to plug this entire argument in for the x that we see in the function. So root x plus h minus f of x, the original function, which is root x, all over h. So now we're at this step. We can plug 0 in for h. We're going to get root x minus root x, which is 0, all over 0. So 0 over 0 means we can go through and factor and find a way to cancel out with this h. So we can go through the conjugate method for numerator, and this will give us x plus h minus x. The x's cancel out, leaving us with h in the numerator and denominator, which cancels out as well. Now we replace the remaining h with 0. So root x plus 0, which is root x. So root x plus root x gives us 2 root x. So our derivative function is 1 over 2 root x. But we want to find the exact slope at x equals 2. So now we can plug 2 into the derivative function, which gives us 1 over 2 root 2. So our slope is 1 over 2 root 2. If we wanted to find the slope of the tangent line, we will simply take our slope and our ordered pair, and then we will plug into our point slope form, which is y minus root 2 is equal to 1 over 2 root 2 times x minus 2. Okay, one last thing. This is just some definition here. Differentiability. In order for a function to be differentiable, so what this means, differentiable means that we're able to find the derivative, that the derivative exists. And visually what that looks like is that it's a smooth curve. Okay, so in order for a function to be differentiable at a point C, it must be continuous at that point. It cannot contain a sharp point, and it cannot have a vertical tangent. So for instance, we can't have a smooth curve, we can't have a curve that's differentiable if there's a hole in the graph, if there's any breaks in the graph. So first off, function has to be continuous throughout in order for us to even consider it to be a smooth curve, or the possibility of a smooth curve. If we have a sharp point, then it's not differentiable. Differentiable just means that we can draw a tangent line to the curve, and here we can't draw a tangent line to a sharp point because there are multiple ways that you can draw a curve, draw a tangent line to this curve and only hit one point. So if we have multiple tangent lines to the same point, then it's no longer useful. So we call that this is unable to be differentiated or not differentiable. Okay. Another way that a function is not differentiable is if there's a vertical tangent. So a vertical tangent means that the slope of that tangent line is going to be undefined because a vertical line does not have a slope that exists.